We left off here. We were talking about diffusion, and we were talking about what is the force that powers diffusion. And it turns out that the force that's making these different molecules or atoms move like hyperactive little blue and red birds, the thing that's making them move is the fact that atoms or all particles are actually jiggling around in space all the time. It's just not obvious. Um, if you look at the table in front of you and it looks like it's holding really still, and in general, the table is holding still. But if we could zoom ourselves down small enough, we would see that even in this apparent solid surface, there are small movements. And there was a guy who discovered this a long time ago. He studied plants, he was a botanist, and he figured out this thing that ended up getting called Brownian motion. This image that we're going to look at, these are um, little droplets of fat that are in milk. And if you look at this, you can see that they are jiggling. Now, if you saw this in the microscope in the lab, you might assume that, just the table is jiggling a little bit. But actually, that's not what's going on. The truth is that these little droplets of fat are being hit on all sides by that jiggling movement of water molecules that we saw in the animation in the previous video. So it is the reason that diffusion happens is actually because of a physics principle, and you don't have to know the name of the physics principle, so I'm not even going to say it, right? But it is good to keep in your mind that all of the atoms and substances on planet Earth appear to act as if they want to go from where those of their kind are more crowded into where their kind is less crowded. So the red birds fly over where there are few redbirds and lots of bluebirds, and the bluebirds fly over to where there are fewer bluebirds and more redbirds. And that is diffusion. All righty. Now, diffusion is used a lot in life. So let's look down here. Whenever you are inhaling and exhaling, you inhale oxygen and you exhale CO2. All the time in your lungs, oxygen, I'll make it the blue one, is moving into your bloodstream as the carbon dioxide, that's a waste product that you want to exhale, is moving into the little air sacs of the lungs. So as blood is going on by, the CO2 is going to go into the lung, and the air from the lung goes into the blood until it reaches equilibrium. So that's just simple diffusion. One of the things that you'll be working through in our lab activities is simple diffusion in different mediums. Mediums are basically the substance that those things are diffusing through. So in a way, kind of like the solvent, except for they don't necessarily dissolve. So there are 3 kinds of mediums that are in this week's lab, and they are a gas, a liquid, and a semi-solid. What we're looking at here is a semi-solid, and that's in this little petri dish is a substance called agar. Agar, you can think of it kind of like a really thick jello. And what we've done in this petri dish is we let some agar harden up, we put little holes in it, and then we dripped into the different holes 3 different dyes. And what we looked at after 60 minutes is how far did the different dyes diffuse through this semi-solid. And you'll notice that the red one diffused very far. It diffused very fast. But let's just focus on the blue one. The blue one did not go as far. Well, if I give you 60 minutes to run and you run farther than your friend wearing blue, then who ran faster? Well, you did, right? If you go farther in 60 minutes, you have run faster. The reason that this red dye diffused faster is one of the principles of diffusion that you need to learn in this week's lab activity. Diffusion is faster with smaller molecules. Knowing that, which of these dyes had the smaller molecular weight, the red or the blue? Well, diffusion is faster with smaller. The red one went farther, so it went faster, so the red one has a smaller molecular weight than the blue. Okay? Diffusion is also faster when the medium is less viscous. So perfume can diffuse faster through air, a gas, than through water, and faster through water than through agar. Viscous. Viscous is basically how thick is the medium. In this little GIF here, the white substance is less viscous than the blue. Viscosity, I often think of it as the quality of how easy it would be to pour it, but it also could be how easy would it be to run through it. You could run from one end of a swimming pool to another faster than you could run through the water of the pool, right? And that has to do with the viscosity of the medium. So diffusion is faster in a less viscous medium. Diffusion is faster at higher temperatures. The reason that I showed you those two videos, the one that was the animation about how things move faster at higher temperatures and slower at lower temperatures, along with Brownian motion, is so that you could visualize that things are being bumped around, and the more they get bumped around, the faster they will diffuse. At higher temperatures, things get bumped around more, not just faster, but farther. So at higher temperatures, things will diffuse faster. Things also will diffuse faster at a larger or steeper concentration gradient. Let me give you an example. Okay, let's imagine I'm going to take a tablespoon of sugar. That's going to be my tablespoon of sugar. It is 100% sugar. Okay. Now, I am going to ask it to diffuse into two different cups of tea. All righty? One cup of tea has got no sugar at all in it. Okay? And one cup of tea already has 1 tablespoon of sugar in it. So 1 cup of tea is, we'll just say it's 20% sugar. That would be a lot of tea, but I mean a lot of sugar in your tea. And this one is 0%. The speed of diffusion, the speed of diffusion going from our 100% tablespoon of sugar into tea with no sugar in it would be very fast. Getting a tablespoon of sugar to diffuse into tea that already has a tablespoon of sugar in it would be slower. And by the way, if you've ever tried to do that, you would actually know that. You probably didn't know that the reason is that the concentration gradient between a tablespoon of sugar and 0% sugar is a steeper gradient than the concentration gradient between a tablespoon of pure sugar into a glass of tea that's 20% sugar. But make sure you know these 4 things. All right, we're going to start the osmosis on video 3.